Hi everybody, this is lecture 5 and today I will tell you all about triple integrals. So let's get to it. I drew a triple integral here on the side. Let's take a look at it. So first you guys can see that there are 3 integral signs. You can see that there is a function of 3 variables, and you guys can see that there is a region of integration denoted down there. So my first remark is that when we do a triple integral, the region of integration should be a solid region in 3D space. So remember that in 2D, when we were doing double integrals, the region of integration was a flat shape in the xy plane. Now, with triple integrals, the region of integration will be a solid shape in a 3-dimensional space. So I drew one such a sample solid region for you guys here on the side. And so, to be clear, we wouldn't do a triple integral over the surface of a sphere, but we could very well do a triple integral over the region inside a sphere. Okay. Now, let's now move on and discuss the definition of the triple integral. So this is a number, right? This is a definite. This integral has both a function and a region specified, so it evaluates to a number. It's an expression complicated expression that denotes a number. Now, what number is this? When we were discussing double integrals, I had a quick answer to give you. I said you have so when we had even single integral, and the answer was just like the answer I gave you when we. The answer you guys learned for the meaning of the single integral. Let's take a step back. So when we have a single integral of a function f of x over an interval of the x-axis of the x line, you have a function f of x. You introduce a new variable y, and then you look at the curve y equals f of x, and you look at the volume below the graph, right? To form the graph, you introduce a new variable y, and you see that new variable is equal to the function that gives you a shape. You look at the area below that shape. Okay, now in 2D, we started with a function of 2 variables, x and y. We passed to the graph, so we introduce a new variable z, and we look at so the graph has equation z equals f of x, y, and we look at the volume below the graph. Now, in 3D, this geometric picture becomes a little bit more complicated because the graph of a function of 3 variables would live in 4-dimensional space, right? To form the graph of a function of x, y, and z, I should introduce a new variable w, and then say that w is equal to f of x, y, z. That's going to give me some set of points in 4-dimensional space, in x, y, z, w space. And then I would look at the, not the volume, but the hypervolume, that's not really working below the graph, right? That's not a notion that translates directly to applications. We could make that work. As a mathematician, it's kind of, maybe I think about it sometimes, but it's not the way triple integrals appear in practice. So I'm just going to give you, instead of thinking about hypervolume and 4-dimensional space, I'll just give you the other. I'll use another definition as our starting point. We'll just use Riemann sums as our starting point. So the Riemann sums approach is the one that talks more closely with applications. So let's work this out. Let's understand. Let's write something here to make clear this idea of Riemann sums. So the integral is going to be defined as some limit of Riemann sums. Okay, so here's how you get a Riemann sum. First, you subdivide the volume, the region of integration, into little pieces. So I drew a little solid piece here. So typically you'd have maybe 1 billion pieces, a very, very large number, whatever large means to you. So you subdivide E into many, many little pieces, and you call, so let's say this is the ith piece, and let's say that it has volume delta vi. Okay, so I is the index that tells me what piece I'm looking at. And so beyond the subdivision, to get a Riemann sum, we need to choose sample points in each of the volumes, each of the parts of the subdivision. So here I chose a sample point. So this is a sample point. And it'll have coordinates. So this is the ith sample point. So the coordinates will be xi, yi, zi. Okay, so to form a Riemann sum, I need to subdivide my region and pick sample points. And then once I've done that, here's what the Riemann sum looks like. I'm just going to add over the various pieces in the subdivision of E, over the various pieces that I broke E, into which I broke E. And then I add the value of the function evaluated at the sample points. So so there is a sum over each piece of the ith piece. I evaluate f at the ith sample point, and then I multiply by the volume of the ith piece. And so once I did all of these multiplications, I add the results together, and this gives me the triple integral in the limit. So this is called a Riemann sum. And here we're adding over all the pieces in the subdivision of my original integral, and we're taking a limit as, let me indicate this in the notation, we're taking a limit as delta vi goes to 0. So here I'm not being very clear about what it means to take a limit as the subdivisions of E become finer and finer. So I'm not explaining what that means, but I hope it has a clear enough intuitive understanding that we're breaking up E into pieces, into subdivisions which are, using subdivisions which are very, very, the resulting pieces, each of the pieces in the subdivision is very, very small. And as soon as they're all small enough, so their diameter is small enough, then the Riemann sum you get for any choice of sample points will be close to a fixed number, and that number is the integral, the triple integral. Okay, so this is these are a few words about the definition. So next thing I would like to tell you is I would like to discuss our applications of this notion. So I kind of took the rug from beneath your feet, right? It took off your because because the interpretation, the most straightforward interpretation of double integrals doesn't work for triple integrals, but it turns out that the other applications, and you can use once you know what a tool is used for, you can use those applications to understand the tool itself. So it turns out that most of the applications of double integrals, just carry over to triple integrals. So I want to go through that. I want to go through those applications and show you and explain how they still work for triple integrals, and you can see what this thing is used for. Okay, so I took the notes. I just want to make a few verbal. I prepared the slides, so I'll just make a few verbal remarks, because this is very similar to the discussion I had maybe 1 or 2 lectures ago. So the first application of triple integrals is for computing volumes of solid regions in space. Right? If you integrate the function 1 with respect to dv, if you do a triple integral of the function 1 over a region, you just get back the volume of that region. Right? Because the thing we have on the right is a limit of Riemann sums. So for any Riemann sum, you're breaking E into little pieces. You're then multiplying the volume of each little piece by 1. So you just get back the volume of each little piece, and you add all these volumes of the constituent pieces. The result is the volume of the whole shape. Okay, so the next application we had for double integrals, and that still holds still works in 3D is that we can use triple integrals to compute masses, the mass of a solid region. So for that, we need to know how much, what's the amount of mass per unit volume throughout the shape. This could depend on the position. This could depend on which point of the shape you're looking at. So in general, we have a density function. It tells you how much mass there is per unit volume at that point. If I integrate this density function over the region, I am multiplying a certain amount of mass per unit volume by a certain amount of volume. This gives me the amount of mass in that little bit of volume. And then I add over all bits, over all pieces that make up E, and I get the mass of the whole shape. The next application we discussed when we were talking about triple integrals was averages. So there, you're adding all the possible values that f takes throughout the region E, but you're multiplying each of these values by certain weights, namely the volume of the region where f takes each value. So really, we're breaking E into a bunch of little pieces. You take a sample point in the piece, evaluate f at that sample point. That tells you that's so you say that f, you're saying that f is taking approximately that value on that little piece, multiplied by the area, the uses weight for the average, the volume of that little piece. You add these values times weights, and then you divide by the sum of all weights. So this gives this average is going to be some number between the minimum and the maximum value of f in the region E. So it's going to be some number between these two, and but it depends. But it's giving more weight to values that f takes over a big portion of the volume of E. Sometimes we want to give more importance, give importance not to volume. So weighted averages are there for the situation where it's less important. So if you can imagine that E was that E was very irregular, and some pieces of it were way heavier than others, and you might want, when you're forming your average, you might want to give more importance to values that f takes in places where E has larger, where the region has a larger density. So if you want to do that, instead of taking the volume as weight, you take the mass of each little piece, and then you divide by the sum of all those masses as your weight. Okay, so to conclude, we still have the other the applications. We still have two more. We still had two more, which we also have in 3D. So we can compute the center of mass of a 3D shape by taking the weighted average of the x-coordinates of all points in the shape, and the weights are given by the mass, by the density function. So a weighted average of the x-coordinate throughout the shape gives you the x-coordinate of the center of mass. Similarly, you have the y and z coordinates of the center of mass. They're weighted averages of the y and z coordinates on the shape. And we can also do moment of inertia in 3D. So for example, the moment of inertia around the z-axis is the triple integral of x squared plus y squared. So this is the distance from the z-axis squared. And then you multiply that distance from the z-axis squared times rho dv, and you integrate. And this gives you the moment of inertia around the z-axis. So for example, the rotational. So as before, the point of this is that the rotational kinetic energy is a half of Iz omega squared, where omega is the amount of radians, is the angular speed. So the angle that's rotated per unit time. That's the angle of rotation per unit time. We can also form compute moment of inertia around any other axis. So, for example, around about the y-axis, the formula becomes so it's noted y. So somehow I want to, in my notation, to indicate the axis I'm talking about, because this changes the number that you get. It's the triple integral of the distance to the distance from the y-axis squared. So that's x squared plus z squared times rho dv. And you could also do the moment of inertia around the x-axis, or even around any axis, but any other axis. But then you need a way to describe that axis and find a nice formula for the distance squared. So as far as homework and exams are concerned, you don't need to worry about that other case. Most of the time, the correct way, the best way to go about this is to choose coordinates that are suitable, that are adapted to the problem at hand. So you can always, if you choose if the rotation is your only concern, you can always make the axis. You put the z-axis to coincide, make the z-axis coincide with the axis of rotation, and then the formula that you need to consider is the one that I first drew. Okay, so this is it about applications. Let me tell you now about how we compute this, compute triple integrals. So our bread and butter will be, like before, will be Fubini's theorem. There are two different ways to apply Fubini's theorem. They come with different geometric interpretations, and sometimes it's better to use one, sometimes it's better to use the other. And so let's get to it. So let's just do it. So here's so let's say we want to do a triple integral over this region here, E on the side. We're integrating a function, some arbitrary function, with respect to dv. Okay, so here's what that integral looks like. We're going to be, so Fubini's theorem for triple integrals tells us that we can evaluate this as a double integral over the projection d of the shape. And then the function, so we're going to be integrating, so this triple integral is equal to a double integral of some function of x and y. And here's the function of x and y. The function of x and y is another integral. So let me draw a picture first. So we're going to be integrating a function of x and y. That function is this. So if you give me a point xy in the plane, I can get I intersect the solid region E with this vertical line segment, and then I do an integral with respect to z up along this segment. So the function of x and y we're integrating over d is the integral for z going from some minimum value depending on x and y to some maximum value depending on x and y. Then you integrate the function f of x, y, z dz. So this is a single integral. X and y are fixed. X and y also appear in the bounds. You integrate up with respect to dz. This is a number, so you get a number that depends on x and y. So you really get a function of x and y, and then we integrate that function over this region D to get a number, and that number, Fubini's theorem is telling us, is equal to the triple integral. Now, let's so in this there are a few things to discuss. So first, at the bottom over here, so this here is what I mean by z min, the minimum value of z in this vertical segment. And this is here is z is equal to the maximum value, some maximum value that depends on x and y. Um, I should note, I should be a little bit more precise about what is this region D. So here's how you get a point of D. You start with any point with a point in the solid region E, and then you forget about its z coordinate. You get a point in the plane. So the points in the plane that you get by forgetting the z coordinate of points in E. So this set of points is called the projection of E. So you can think of it as the shadow that E casts onto the xy plane. So D is this shadow, this projection of E onto the xy plane is the domain of this double integral. And yeah, that's it. Also, I should note one thing, that I drew a nice region where this vertical segment had a single piece. Right, so here I had a single piece rather than two vertical. So when I draw a vertical line and intersect it with my region E, I got a single vertical line segment. If I had multiple line segments, I would, in principle, have to have multiple integrals inside. Most of the time, so you would add integrals over each individual segment. That's, if you see something like this, it's probably a bad sign. It's usually a bad sign. You most likely want to break up if you have a complicated region. So for example, something like this, and then you draw a vertical line segment. So you draw maybe a different line is the one I want. So if I have something like a torus, a solid donut, and I draw this vertical line segment, I get this vertical line. It meets the region in two line segments. So in this situation, I have two integrals inside. If you see something like this, what you really want to do is to break your region in two. So integrate over the top half first and then over the bottom half, so as to avoid the whole situation. Okay, so the integral inside is not yet ready to be evaluated. So to evaluate it, we have to set up the integrals, the double integral as an iterated integral. So let's do that. So we're going to write it as an integral in the order dz, dy, dx. So it'll need bounds for x, bounds for y, bounds for z, and then I'll integrate f. I'll integrate the function. Okay, so let's find the bounds for x. So they're going to look something like this. So I'll have a minimum value of x in my projected region D, and a maximum value of x in the projection region D. So this minimum value, these extreme values for x in the projected region are the same as the extreme values for x in the whole shape, right? Because the values of x that you get in this region are, so remember, points in D are the x and y coordinates of points in E. So the extreme values of x and y in D are the same as the extreme values of x and y in the whole shape E. Okay, so we start, the outer integral goes from x min to x max. Right, we're setting up here a double integral over D. And then we fix an intermediate value of x between x min and x max, and we intersect our region D with this line, with this copy of the y-axis, but where x is equal to the value we fixed rather than 0. And then the inside integral, the bounds for the inside integral are here, are these numbers over here. So we have y min in terms of x and y max in terms of x. And you guys can see that these minimum and maximum values for y, they depend on which x I fixed. If I had chosen this x, I would get this segment, and then the minimum value would be this, and the max value would be that, would be different. Okay, so we have minimum value of x and maximum value of x. So let me write this on the integral on the side. So y min of x, y max of x. And finally, the z integral, well, we had already set it up before, so let me just rewrite it. So the z will be integrated from some minimum value that depends on each x, on points x comma y in the region D, and the upper bound for the integral also depends on a fixed point of the region D. Then we integrate the function f of x, y, z. Let me omit the argument for the time being. So f times dz dy dx. So this is the form where the integral is ready to be evaluated. This form over here is usually one good geometric way to find the bounds that you end up evaluating. So you think of it in terms. So first you ask yourself, what's the projection of my region onto the xy plane? So that's going to be a 2D shape. It's usually easier to describe than a 3D shape. Then, once you know the projection, you ask for each point in the projected region, what is this vertical line segment? And then you use this, first, is there a single vertical line segment? Usually the answer will be yes, and then you just have to find the formulas for the lower bound and the upper bound of the segment. So, but I want to stress that the equation in the middle, even though it's not the thing you evaluate, it's the way you get the bounds at the end. It's a useful intermediate step to getting the bounds. Here's another, so what I would like to do is show you now another intermediate step, an alternative intermediate step to getting the same, to getting the iterated integral that you'll eventually evaluate. So this is, so it uses a different picture. So instead of working with the projection onto the xy plane, you work with the slice, with various x slices. So here, let's say, so you can see that I fixed a value of x. Let me form an x slice of my 3D shape E. So if I fix x and intersect E with the copy of the yz plane with that fixed value of x, I'm going to get a shape that looks like this. Right, so this is a region, so this I get this blue region of a copy of the yz plane that instead of having x equal to 0 has x equal to, well, this fixed value that I'm also calling x. Okay, so now notice that the two integrals inside, so the two integrals inside, they describe an integral over this region, right? So before, the way we got these bounds to begin with was first we found the inner bounds by choosing points in D and going up, and seeing where we intersect the region D. And the way we found these other two bounds was we looked at just the region D itself, just at this projection. And so these two integrals just describe this double integral. Now, it turns out that the other two integrals, they also describe a double integral, and the double integral is over this x slice. So let me write down the formula that will be useful. So this whole thing can be rearranged as an integral from between extreme values of x and the whole shape, and then for an intermediate value of x, you integrate a double integral. So you integrate over the x slice the function f with respect to dz dy. So the area, dz dy is the area element in this x, in this blue x slice, and then finally you integrate with respect to x. So there are two ways to put brackets. So we have three integrals. If I put brackets like this, I'm doing a double integral of a single integral. If I put brackets like this, I'm doing a single integral of a double integral, and the double integral we're doing is double integral over this slice over here. Right? Let's try to see that in more detail. So why is this so certainly so these bounds here, for these bounds, they depend on x. So you fix a value of x, then you integrate y from some minimum value of x to some maximum value of x, and then for each value here, z goes up from some minimum value of z and then to some upper value like that. So you see that I get all of these vertical lines like that, and this does indeed give me the slice that I drew. All right. Now let's do an example calculation, and I think that will be just a sec, please. Oh, I'm not timing. I think that will be enough for today. So let's do that. So here's the problem. I give you a shape, and it's a three-dimensional region of R3, and it's this. Our job is to compute its volume. So the region is described by these inequalities. So the first order of business is to draw it to get a sense of what's going on. So here's the picture. Start with the axes as usual. It's a good idea to draw the axes always using the same convention. So you have one fewer thing to think about. Now we have two shapes. So z is between two extremes. The one extreme is where z is equal to this lower bound, and the other extreme is where z is equal to this upper bound. So z equal to the lower bound is a familiar shape. Z equals x squared plus y squared is a paraboloid. So here's what it looks like. So down here, z is equal to x squared plus y squared. And on the upper shape, on the upper bound, z equals 4 minus x squared minus y squared is also a familiar shape. It's so there's a constant, it's shifted up, and there's a minus instead of in front of x squared plus y squared. So it's an upside down paraboloid lifted so that the top has z equal to 4. So up here, z equals 4 minus x squared minus y squared. And at the top, we get so if x and y are 0, z is equal to 4. So this top value, this top point is 0, 0, 4. Okay, so let's set this double integral up. So we are going to work over, so the triple integral. Oh, I have to decide, oh, we want the volume, right. So the function we're integrating is the function 1. So the volume of E is equal to the function 1, and that's also, so now we can set up this triple integral. It's going to be a double integral over the projection of E onto the xy plane. So here's that projection. So there's D. It doesn't look as good as it could. It's actually a circle, so it looks pretty bad. But now we're going to do an integral with respect to z from some lower value to some higher, to some upper value, right? So for an intermediate value, if I take a point in the xy plane, z will be integrated up this vertical slice, up this vertical segment that I just drew. So z starts at the bottom paraboloid where it's equal to x squared plus y squared, and it stops at the upper paraboloid where it's equal to 4 minus x squared minus y squared. And then you integrate the function 1 with respect to z dA. We can even evaluate the inner integral before deciding what this shape d is, what this projection d is. So we have the double integral over d of the integral of 1 dz is just z. So evaluated between these 2 points, I get 4 minus 2 x squared plus y squared, like this. Okay, Now we have to decide, we have to look at the region D, this projection onto the xy plane, the projection of our original solid shape onto the xy plane. And a way to get a hold of it is to notice that this curve over here, the projection of this curve, gives me the boundary of this region D of this projection. So let's look at what this curve is. So on this curve, this curve here, where the two paraboloids meet, is characterized by the fact that z is equal to 4 minus x squared minus y squared, but also z is equal to x squared plus y squared. So on this curve, on these two curves, I know that 4 minus x squared minus y squared is equal to x squared plus y squared. In other words, so x squared plus y squared is equal to, so therefore x squared plus y squared is equal to 2. And so the radius, so the root of x squared plus y squared is equal to root 2. So on this red circle and on the blue circle, well, we conclude that the red circle, that this red curve and this blue curve are both circles, and the radius of the two circles is equal to root 2. So r is equal to root 2. Okay, so we have a double integral. I have a double integral of this function over a disk. So in the region inside a circle, which is a disk, you can see, so the disk certainly can be easily described using polar coordinates, and also the function we're integrating is easy to describe using polar coordinates. So let's just change to polar coordinates. So we're going to get an integral in theta. Here we have the whole disk, so theta goes from 0 to 2 pi. R, the radius, goes from 0 to the radius of this disk, which is root 2 in this case. And we're integrating the function 4 minus 2 times r squared times r dr d theta. So r dr d theta is dA. Okay, so let's do it. So first, can you guys see that this part here, the integral with respect to r, is neither the bounds nor the function we're integrating, function of r we're integrating, neither depend on theta, so the answer of this inside integral is going to be a number. It won't be a function of theta. So it's we can pull out this integral, and then the theta integral will just evaluate 2 pi, and multiplied by whatever is the integral of the thing inside. So the thing inside evaluates to, so we have 4r dr. This evaluates to 4 times r squared over 2 minus 2 times r cubed, which evaluates to r to the 4th over 4 between 0 and root 2. That's 2 pi times 2 times root 2 squared. That's 2 minus 1/2 times root 2 to the 4th power. That's 2 squared, that's 4. And so let's see, here we have 4 minus 2, that's 2. Here we have, before we have 2 pi, so multiply 2 pi by 2, we get 4 pi. And that's the value of the integral. And voila, there you go, that's our first triple integral. So you can see that getting the number in the end takes some work and involves interesting geometry. All right, so thank you very much. Thanks for listening. This is what I had to say today, and I'll see you guys next time.